Hello again, and welcome back to Chapter 6. Today we're going to look at 6.4, which is the first order linear differential equations. The objectives of this section are to solve a first order linear differential equation, as well as use these linear differential equations to solve the applied problems. A first order linear differential equation states that an equation of the form dy dx plus some function p of x y times y is equal to another function q of x. P and q are both going to be continuous functions of x, and this first order linear differential equation is said to be in standard form when it looks like the above format. To solve a linear differential equation, the first thing you want to do is you want to write it in standard form so that you can identify your p of x and q of x. Once you identify p and q of x, then you want to integrate p of x in the form of the expression u of x equals e raised to the integral of p of x d of x. This is what we call our integrating factor. The general solution of your equation then is y equals 1 divided by u of x, which is your integrating factor, times the integral of q of x times your integrating factor times d of x. And this is our general solution. For example 1, we want to find the general solution of y prime plus 2 divided by x times y equals 3x minus 5. The first thing I'm going to do is I'm going to rewrite my y prime as dy dx plus 2 divided by x times y equals 3x minus 5. And as we mentioned on the previous slide, our goal is to write this in standard form so that we can go through and identify our p of x and q of x. Now in this case, we actually happen to be in standard form. I have my dy dx, which is given right here, and then my p of x is really this function here that occurs before the y, and q of x then equals 3x minus 5. So we'll say p of x is equal to 2 divided by x, and q of x is equal to 3x minus 5. Next, I want to go through and find my integrating factor. And the integrating factor, if you recall, was equal to u of x, which equaled e to the integral of p of x dx. Okay, so if I rewrite this, this is really equal to e raised to the power of the integral of p of x, which we said was 2 divided by x dx. And if I integrate 2 divided by x dx, this really gives me e to the power of 2 times the natural log of the absolute value of x plus c. Now when I go through and I actually simplify this, if you recall, I can rewrite an exponent that has a coefficient in front of it as a power. So I'm going to rewrite this as e to the natural log of the absolute value of x squared plus c. And my e and natural log are going to cancel, so this is going to leave me with the absolute value of x squared plus c. Now it doesn't matter if I have a negative or a positive number in the absolute value, because once I square it, it's going to become positive. So that's just going to give me x squared. Now, to find my general solution, I'm going to use the equation that was given to me before, which was y equals 1 divided by u of x times the integral of q of x times u of x dx. So I'm just going to plug in everything that I've been given. So 1 divided by u of x, which was actually x squared, times the integral of q of x, which we said was 3x minus 5, times u of x, which we said was x squared, d of x. When we go through and simplify, we have 1 divided by x squared times the integral of 3x cubed minus 5x squared dx. When I integrate, I end up with 1 divided by x squared times the integral of 3x cubed is going to give me 3/4 x to the 4th minus 5/3 x cubed plus c. And then the last thing I can do is I can simplify, or just by distributing the 1 over x squared. So that will give me 3/4 times x to the 4th divided by x squared minus 5/3 x cubed divided by x squared plus c over x squared. So I end up with 3/4 x squared minus 5/3 x plus c divided by x squared. And this here would be my final general solution. Now, Theorem 6.3, which is the solution of a first-order linear differential equation, tells us that an integrating factor for the first-order linear differential equation, which we said was y prime plus p of x times y equals q of x, is u of x equals e to the integral of p of x dx. We made note of that in the right before the first example there. Now, if we want to find the solution of that differential equation, we're going to go y times e to the integral of p of x dx equals the integral of q of x times e to the integral of p of x dx plus c. This isn't something that you're going to have to memorize. The only thing you're going to have to remember is that when you multiply by the integration factor, this is really converting the left side into the derivative of the product of y times e to the integral of px dx. Example 2 says to find the general solution of x, y prime minus 2y equals x, and that should be x squared. I apologize. We are going to want to go with the standard form of the given equation, the y prime plus pxy equals qx. And in this case, we're going to have to write this equation here in that form. So right now I have x times dy dx minus 2y equals x squared. Now the one thing that's keeping my equation from being in the standard form is this x right here. So to get that out of there, I'm going to have to divide everything by x so that I'm left with just a dy dx. So if I divide everything by x, I end up with dy dx minus 2 divided by x times y equals, and then x squared divided by x is just x. So now I know that p of x is really equal to a negative 2 divided by x, and I know that my q of x is really equal to x. I now need to go back and find my integration factor, which was e to the integral of p of x dx. So when I do that, I get e to the integral of a negative 2 divided by x dx. And when I integrate that, I end up with e to the negative natural log of x squared. Now, when I know that when I take the e of a negative natural log, then I'm going to end up with, because this is really 1 over e to the natural log of x squared, and then e to the an e raised to the power of a natural log is going to give me 1 over x squared, and this is my integration factor. Now, the general solution that was given a while back said that y was equal to 1 divided by u of x, which was our integration factor, times the integral of q of x times u of x, which is our integration factor, dx. So if I plug in everything I know that I have y equals 1 divided by 1 over x squared times the integral, we said q of x was really equal to x, and u of x again was equal to 1 divided by x squared times dx. Now when I simplify this, I end up with 1 divided by 1 over x squared is just x squared. So this is y equals x squared times the integral of 1 divided by x dx. And for simplification purposes, right now let's take this x and put it over on the other side so that we have just an integral on one side and everything else on the other. So I'm left with y divided by x squared equals the integral of 1 over x dx. When I integrate this, so y divided by x squared is equal to the natural log of x plus c. Now to isolate my y value, I'm just going to get rid of this x squared here, and because I'm dividing, I'm going to multiply both sides by that, and I end up with y equals x squared times the natural log of the absolute value of x plus c. And this would be my final general solution. Now we're going to look at the applications. Right now we're going to look at the falling object model with air resistance. So far in all of the problems that we've done that have dealt with falling objects, we have neglected the air resistance. We haven't even recognized it as even being a part of a factor, or being a factor in the problem. Now we're going to include it. We know that air resistance is proportional to velocity. So if g is a gravitational constant, then the downward force F on a falling object of mass m is given to us by mg minus kv. Now that's mass times your gravitational constant minus some constant k times your velocity. Now Newton's second law of motion states that our force is equal to mass times acceleration, and we know from previous sections that acceleration is really the derivative of velocity with respect to time. So I can actually set this up as mass times acceleration, which is dv dt, is equal to mass times a gravitational constant minus a constant times our velocity, which is also equal to the derivative of velocity with respect to time plus that constant times velocity divided by mass, and all of this is equal to gravity, or the gravitational constant. So let's look at example 4. It says an object of mass m is dropped from a hovering helicopter. We want to find the velocity as a function of time. Assume that air resistance is proportional to the object's velocity. Because air resistance is proportional to the object's velocity, I know that dv dt plus k, which is my proportionality constant times velocity, divided by my mass, is equal to gravity, or the gravitational constant. Now right now, because I know that my constant of proportionality k is not going to change, and I know that the mass is not going to change, I'm actually going to take just some arbitrary letter, which I'm going to call b, and set that equal to k over m. And the reason I'm going to do this is going to be a little bit easier for me to identify or use the method of separation of variables. So when I do that, I end up with dv dt plus b times v. And again, b is really equal to the k over m piece right here, and we're going to set all of this equal to g. Now, in order to separate my variables, the first thing I'm going to do is I'm going to go dv dt is equal to g minus bv. Then I'm going to multiply both sides by my dt, and that's going to give me dv is equal to g minus bv times dt. Okay, now because this g minus bv term has no t's in it, but it has v terms in it, I know that for separation of variables, I need to get that over on the other side with my dv term. So I'm going to divide both sides, and I'm going to end up with 1 divided by g minus bv times dv is equal to dt. And from here, I can integrate. So when I integrate both sides, I end up with a negative 1 divided by b times the natural log of the absolute value of g minus bv, and this is equal to the integral of dt is just t plus c. Now, I want to clear out that fraction, that negative 1 over b, so I'm going to multiply everything by a negative b, and when I do that, I end up with the natural log of the absolute value of g minus bv is equal to a negative bt minus bc. Now I'm going to raise everything, or take e and raise it all to the, so I'm going to go e to the power of the natural log, and then e to the power of the negative bt minus bc. And this is going to give me g minus bv is equal to ce to the negative bt. Now, since our object was dropped, we know that the velocity equaled 0 when our time equaled 0. So using that, we can go in and we can solve for our value of g, because then I end up with g minus b times 0 is equal to c times e to the negative b times 0. I know that this whole piece here is going to become 1, so I know that g then equals c. So with that, I know that wherever I have a c into this above equation right here, I can really plug in a g. So let's go ahead and do that. So I end up with a negative g minus bv is equal to ge to the negative bt. Now, my ultimate goal was to find velocity. In order to find velocity, I need to get the v term by itself. So to do that, I'm going to subtract the g from the left side and then divide by the negative b. So that's going to give me negative bv is equal to a negative g plus ge to the negative bt. Then I end up with v equals g divided by b. So g divided by b. And then I have a positive ge to the negative bt divided by a negative b. So this is going to become minus ge to the negative bt divided by b. And I know that b, we said, was really equal to k divided by m. So when I go ahead and I plug in that into my equation, we end up with v is equal to g divided by k divided by m minus ge to the negative bt divided by k divided by m. Now when I divide a fraction by another fraction, I can really multiply by this reciprocal. So this really gives me gm divided by k minus gm divided by k, and this is all multiplied by e to the negative bt. So if I factor out that gravitational constant mass times the mass divided by the constant of proportionality, I end up with gm divided by k times 1 minus e to the negative bt. Oops, and I'm sorry, I forgot to plug in the k over m into our exponent here, so we'll do one more step. And that was v is equal to gm divided by k times 1 minus e to the negative kt divided by m. And that's the equation for our velocity.